is about free energy and entropy. And these topics are probably going to feel a bit obscure. There's a lot to these topics. They are fairly complex. I just want to focus on this last video on, getting you a brief introduction and overview of these. So we're really just going to talk through them. I want you to hear them. I want you to be able to begin to apply them. But really, it's just to get you one quick introduction to these so that you've at least heard them and thought of them before. So let's start by talking about spontaneous reactions. Some of the energy that's released in a chemical reaction can be used to do work. Your car uses a chemical reaction, the ignition of gasoline, to push pistons in your internal combustion engine. So it's a chemical reaction, energy is released, and it's used to do work. It's used to move something. And the energy that's available to do that work is called free energy. Free energy is the available energy. The whatever is available to us to harness out of a chemical reaction to apply elsewhere. So when we say spontaneous reaction, that's a reaction that happens spontaneously. That implies that there are non-spontaneous reactions. So remember, we can write a balanced equation for pretty much anything. Any reactant, we can write an equation for it, we can balance it, but that doesn't mean that that reaction is going to take place. I can write you a balanced equation for carbon dioxide decomposing into carbon and oxygen. That doesn't mean it's going to happen naturally, right? Rarely do we see carbon dioxide gas spontaneously breaking up into solid carbon and oxygen, right? We know there's carbon dioxide gas in our air, lots of it. We never see solid carbon raining from our sky as the carbon dioxide breaks up. That doesn't occur, at least not naturally. The other direction, though, we know does occur. We know that solid carbon and oxygen will react to make carbon dioxide. And so in one direction, this reaction is non-spontaneous. In one direction, it is spontaneous. In the direction as written, this is not something that occurs naturally. It's not something that just happens spontaneously. We would have to force it. And so that's the difference between a spontaneous and a non-spontaneous reaction. So all the balanced chemical equations that we could write, we'd divide into two groups. We'd have the spontaneous reactions, the ones that naturally occur spontaneously without our help, they happen, and the other half of non-spontaneous reactions, the ones that either don't occur or don't occur efficiently or don't occur at our conditions, ones that you would have to force to react. So a spontaneous reaction is a reaction that occurs naturally and favors the formation of products under a given set of conditions. If it's spontaneous, it means that the reactants are going to form products. That is a favored process. So for example, we've got a picture of fireworks here. This is a highly favored spontaneous reaction. It's a combustion reaction. We burn reactants, we form the products, it releases a lot of heat, a lot of sound, a lot of energy. And so we produce products and we also release free energy. We release a lot of energy in spontaneous reactions. Meanwhile, a chemical reaction that does not favor the formation of products under a given set of conditions would be non-spontaneous. These reactions would form very little, if any, product. They just don't happen naturally. Now, in nearly all reversible reactions, one direction is favored over another. When I say reversible reactions, I mean these equilibrium reactions that we've been writing for this past unit. And we saw a bit with the solubility and a bit with the equilibrium constants that just because something's in equilibrium doesn't mean we have an equal amount of product and reactant. Typically, one of these directions is more favored. One of these directions is spontaneous. So looking at this example on here, we've got the decomposition of carbonic acid, and that forms over 99% product. The forward reaction is spontaneous. Forming products is favored. The reverse reaction would be the non-spontaneous one. That's not very favored. And so our forward one releases free energy. The reverse reaction, carbon dioxide and water recombining to make carbonic acid, would be non-spontaneous. It wouldn't happen naturally to a large degree. We could force it, but it wouldn't be a spontaneous reaction. Another example, if we mix cadmium nitrate and sodium sulfide, the products are aqueous sodium nitrate and a solid precipitate of yellow cadmium sulfide. And so we have this reaction written here, again with the two-way arrow, because it is reversible. It does establish an equilibrium. But the forward reaction is the spontaneous one. This one is favorable. We form lots of product. The reverse reaction is non-spontaneous. We really aren't able to effectively take this cadmium sulfide and break it apart, dissolve it in water to make these compounds. It doesn't really go that way. Once the solid precipitate is formed, it pretty much, for the most part, remains a solid precipitate. That's not to say we can't undo it, because if you have enough time and energy in chemistry, you can force most reactions to happen, but it means it's not spontaneous, it's not natural. One important thing to keep in mind is that spontaneous and non-spontaneous tell you whether something is favored. They don't tell you anything about its rate. We also talked about rate this unit, and so we've seen that the rate of a reaction can vary greatly. It can be near instantaneous, where the reaction happens in a matter of milliseconds, or it can be on the scale of millions of years. In the case of, I believe we talked about carbon forming diamond earlier, perhaps. And so just because a reaction is spontaneous and favored doesn't mean it's particularly fast. The spontaneous reaction could be so slow that it appears non-spontaneous. It appears that nothing's happening. And that's not true. It's a favored reaction. It just has a very slow reaction rate. So you can't necessarily base your categorization over your observations. Sometimes we'll have to do calculations there. One other important thing is that spontaneous and non-spontaneous are true only for a given set of conditions. Sometimes you can change the condition and a non-spontaneous reaction will become spontaneous. For example, temperature is a very easy condition to change. There are tons of reactions that won't occur naturally at room temperature, but if you heat them up to 200, 2000, a certain degree Celsius, they become spontaneous. One great example to talk about is photosynthesis, and this applies to a lot of the concepts we're going to talk about today. This is a multi-step reaction. As you know, it takes place in plants, and so if you were just looking from outside the plant, your outside observation would be that the plants bring in carbon dioxide and water, and they produce sugar and oxygen. That's the overall process of photosynthesis. Right? The plants bring in carbon dioxide from the air, they bring in water from the ground, and through the process of photosynthesis, in the presence of light, they produce sugar, their fuel, and they produce oxygen gas. Now, this is a complex process, as it says. It's a multi-step reaction. There are many intermediate steps in there to make that possible. But if we just looked at an overall reaction, we would see this carbon dioxide and water making sugar and oxygen. Now that is not something that would normally occur. We can't do that outside of a plant, right? We've got carbon dioxide and water, again, carbon dioxide in our air, water vapor in our air, we don't see them just spontaneously combining to rain down sugar on us. That's not something that we see happen naturally. But in a plant, there is energy supplied by sunlight and the plant pigments like chlorophyll. There's a set of conditions in the plant that makes this process spontaneous, and it's a set of conditions that just doesn't exist for us elsewhere. Another topic that goes into this is the idea of a coupled reaction. Sometimes non-spontaneous reactions can be made to occur if it's coupled to a spontaneous reaction. Let me show you what I mean. One reaction will release energy, and that energy is used by the other reaction. So one spontaneous reaction releases free energy, and what would normally be a non-spontaneous reaction can use that released free energy to force the reaction, to apply the reaction. And so then they both occur under those conditions. This is a really common process in a lot of our biological systems. So let's do a quick review question. Which of these following statements is always true of spontaneous reactions? You've got A, they produce heat and are not reversible at the stated conditions. B, they release free energy and favor the formation of products at the stated conditions. And C, they are coupled with a non-spontaneous reaction and are easily reversible at the stated conditions. Now the one that is always true here is B. A spontaneous reaction will always release free energy. That's part of the definition of being spontaneous, and it will always favor the formation of products under the given conditions. Those are pieces of the spontaneous definition. A doesn't have to be true. A spontaneous reaction doesn't necessarily have to produce heat, and we'll see more on that later. And spontaneous reactions typically are reversible. The reverse reaction may not be spontaneous, but the reaction is considered reversible. C, spontaneous reactions don't have to be coupled with non-spontaneous. They can be. It's a special set of conditions, but they don't have to be. A spontaneous reaction can be spontaneous on its own. It doesn't need a coupled reaction with it. All right, so that was the free energy half. We also need the concept of entropy. And there's a lot to talk about with entropy, but the main takeaway is that entropy is chaos. Entropy is a measure of chaos. That's really all you need to know. We're going to talk more about it and describe it and provide some examples for understanding. But the key point is that entropy is chaos, and the universe likes chaos. The universe wants more chaos. So let's see how this affects our reactions. If we were just looking at free energy, you might come to the conclusion that only exothermic reactions are spontaneous, because we said spontaneous reactions release free energy, and we know that exothermic reactions are releasing heat, which is a form of energy. But we could come up with some example processes that are spontaneous even though they absorb heat. Let's look at an example. When we see ice melt, we know that for ice to change from a solid to a liquid, it has to absorb 6 kilojoules of heat. From our past unit, that's our heat of fusion. Heat's needed. That's an endothermic process. We need the ice to absorb heat in order to melt. So if we were only looking at enthalpy changes, it'd be difficult to explain why this happens spontaneously. Right? If we set an ice cube out at room temperature, it's going to melt. We didn't have to do anything to it. We'd consider that a spontaneous process. And so we run into that question. Well, it was exothermic, so how is it releasing any free energy? And the answer comes from entropy, right? We need another factor. Enthalpy is not enough on its own to explain why that was spontaneous. We need another factor, and that's going to be our entropy. It's related to the order of a system. Like I said, you can think of entropy as chaos. Entropy measures the disorder of a system, the amount of chaos in it. And there's a law of disorder that states that the natural tendency is for systems to move in the direction of increasing disorder or randomness. The short way of saying this is that the universe favors chaos, right? I mean, we know that. How much energy does it take to keep a room clean? Way more than it takes to let the room get chaotic and messy. Natural processes in the universe tend to create more chaos. For some reason, we won't get into this now, the universe is moving in a direction of chaos. All natural processes, to be natural, are increasing our chaos in the universe, our disorder, our randomness. And so back to that example with the ice. We'll get into this again in a moment. But the reason that going from a solid to a liquid, from our ice to water, was spontaneous is because it increased the chaos. It increased the disorder. Try and picture in your head the atoms in an ice cube. All right? We know in solids, atoms have a really rigid pattern, right? They're right next to each other. They've got their crystal structure. They've got the place they're supposed to be. In a liquid, the atoms have a bit more freedom. They can move around. They can slide past each other. They can be more random, more disordered, more chaotic. And so when the water went from a solid to a liquid form, its amount of disorder, randomness, chaos increased, and the universe likes that. So that process is spontaneous because we ended up getting more chaos out of it. Here's another example just to sort of bring this into an applicable example. So think about dogs. In this first picture, all the dogs are on a leash. They're strolling along in a pretty orderly fashion. We know that that's not a typical situation, right? It takes a lot of training for a whole group of dogs to do that. The natural, more spontaneous situation would be all the dogs not on leashes, running around freely in all directions in complete chaos and disorder. That's more likely to occur. The universe has that one as a more natural tendency. The more disorder, the more chaos is more likely to occur. So, we now have entropy that we can consider when looking at the direction of a reaction. So a reaction in which entropy increases tends to be favored. Now, how can we know if a reaction is increasing entropy? There are a couple things we can look at. The phase of the substance matters for entropy. This is one of the key ways to figure out if entropy is increasing or decreasing. In this picture, we've got a representation of what atoms look like in a solid, in a liquid, and in a gas. And I think it's pretty clear you can see that we have increasing entropy as we move through these phases. Solids, not a whole lot of chaos there. They're very ordered. They've got their pattern, their structure. Everything's in its place. Liquids, little more chaos, right? The atoms are sort of dispersed. They can move around a bit. Gas, tons of chaos, right? Those atoms are moving really fast. They've got no ties to anything else. They can move wherever they want to, spread out to fill an entire room. Tons of opportunities for randomness there. So when it comes to predicting entropy and which direction is favored, really what it's going to come down to is the side with more moles of gas on it. The gas has so much more chaos potential than the liquid and the solid that the liquid and the solid really don't matter at all for chaos. We can just ignore those. Gases are where the chaos is at. Another one, if we crush a substance up, it gets a bit more disordered. Or dissolve a substance when we break it into smaller pieces. Look at the order in this first picture, this brick here. Again, everything's in its place. It's stable. It's not able to move. It's got neighbors holding onto it, keeping it in place. It's pretty ordered. If we crush it up, we've got lots of small pieces now that can have more disorder to them. This is especially important when we're dissolving something. because if we've got a solid sitting in a jar of water, there's not a lot of chaos there, right? Everything in the solid is stuck. It's stationary for the most part. It's got its place, its pattern. But when it dissolves, all those atoms break up and are able to float freely around the water. That's a ton of chaos. They can move wherever they want now. Let's see, another one. So in general, entropy would increase in a chemical reaction if the total number of product molecules that exist as a gas is greater than the total number of reactant molecules that exist as a gas. Or if we're not producing gases on either side when the total number of molecules in the product is greater than the molecules of the reactant. So entropy increases if we make more things. All else being equal, if everything's a solid, then the side that has more compounds, more different compounds, is a bit more disordered. Typically, what's really going to come into play, though, is the side with more gas molecules, because again, the gases are just a huge factor. They have so much more chaos potential than everything else. So in this example, we've got a representation of the process of electrolysis, which is liquid water being split into hydrogen and oxygen gas by running electricity through it. We can see this process required an energy input. We had to input electricity. So it wasn't favored on that front. However, we go from having 2 moles of liquid to 3 moles of gas. We've got 3 moles of gas over here, 0 moles of gas over here. It's all liquid. So this is highly entropy favored. We've got way more chaos and disorder over here because of all the gas molecules that were produced. Entropy will also typically increase when temperature increases because, again, think about your atoms. If you increase the temperature, then you are giving more kinetic energy to those atoms. They are able to move faster and faster and faster, which makes for a more chaotic system, right? If things are moving really slow, you can sort of predict where they're going to be. That's not very chaotic. If they're moving super fast and bouncing off all the walls and bouncing off each other's and they're too fast to ever keep track of or pinpoint, well, that's a lot of chaos. That's a lot of entropy. Let's look at this example. We want to know which of the following would have an increase in entropy for the system, for the reaction. So there's 4 reactions. See if you can figure out which one would have the largest entropy increase. So you can pause and try and think through that. What you should be looking for is which system is creating the most chaos. So which system has the greatest increase in moles of gas. So let's look at this. In A, we have 0 moles of gas in our reactant, and 3 moles of gas in our product. So we've got 3 moles of gas being produced. That one will increase our entropy. Here we've got 3 moles of gas in our reactant, 0 in our product. Oh, moles of gas is decreasing, so entropy is decreasing here, not this one. Here we've got 6 moles of gas in our reactant, 3 moles of gas in our product. Again, moles of gas decreased. Doesn't matter what the liquid is doing because the gas phases have so much more disorder that the liquid's not even comparable. We're just ignoring it. So again, entropy is decreasing here because we're losing moles of gas. Here we've got 1 mole of gas in our reactant, 0 in our product. So moles of gas decreased, entropy decreased. A was the only one where the moles of gas increased in the product, so that's the one that has our entropy increase. So we've talked about 2 factors, enthalpy and entropy. These are the 2 things that are going to determine whether or not a reaction is spontaneous, and we do need to take into account both. If the enthalpy change is really, really big, if it's just releasing a ton of heat, then we can get away with the entropy being not favorable. right? If we're releasing a ton of heat, but chaos is going down a little bit, fine. The universe will deal with it. We're releasing so much energy, we can ignore this. Same thing, if we're getting so much more chaos out of a reaction, but it's endothermic, fine. If this number is just gigantic, it's gonna outweigh this one being non-favorable. Of course, the best case scenario would be an exothermic reaction that releases a ton of energy. That also increases our amount of chaos. That way they're both favorable. And so what we're going to come to is a equation, a way to compare the two changes to figure out what's going to happen. So the size and direction of enthalpy changes and entropy changes together are used to determine whether we have a spontaneous reaction or not. We have to account for both factors. So if we have an exothermic reaction in which entropy increases, we've got a reaction that's always spontaneous. Both these factors are favorable. It's releasing heat, which is energy, and it's increasing chaos. It's the perfect reaction. It is always spontaneous. A reaction can be spontaneous if a decrease in entropy is offset by a really large release of heat, or if an increase in enthalpy is offset by a really large increase in chaos. So even if it's endothermic, but it really increases the chaos, that's okay too. So these are two situations where there's sort of a balance between these two factors. Here's a table to summarize that. So we've got our enthalpy change, our entropy change. Now, if we've got exothermic and increasing chaos, we have a reaction that's always spontaneous. If we've got an entropy change, this one would want to be spontaneous, but it's endothermic, which means as far as enthalpy changes go, we've got non-spontaneous. This one's only favorable, only spontaneous if this enthalpy change is small. It's offset by a really big entropy change. If the enthalpy change is exothermic, so this is favorable, but we're creating less chaos, our entropy is decreasing. This is only favorable if the entropy change, this unfavorable decrease in chaos, is offset by a really big change in heat. A lot of energy is released. Now, if we've got an endothermic process that also comes with a decrease in entropy, that reaction is never going to be spontaneous. There's not a single good thing about it that the universe likes. It's just a rejection. Always no. The universe is not allowing that reaction to happen spontaneously ever. You will always have to force it because it doesn't do anything for the universe. The universe has no reason to let it go. Let's look at this example. Would this reaction be spontaneous? Here we have a solid decomposing to produce another solid, an oxygen gas. So entropy-wise, it's favorable. We're producing moles of gas. So entropy increases for the reaction. We're told that it's exothermic, so we've got an entropy increase and an exothermic reaction that hit both factors are favorable. So this reaction is always spontaneous. So let's go back to free energy. That's what we started talking about. We're going to introduce a term for free energy called delta G, and that's what we're going to use to determine spontaneity. That way we don't just have to go by those vague terms of, well, was the enthalpy change large enough? Not sure. This will let us calculate it exactly. Free energy also goes by the term Gibbs free energy, thanks to the wonderful Mr. Josiah Gibbs, who defined this thermodynamic term. This just had to be the greatest nerd in history. I mean, look at the name. He's got everything he needs. And being a great nerd who contributed to thermodynamics, he naturally named this term after himself, as all nerds do. So the symbol for the Gibbs free energy is G. And free energy, as we know, can be released or absorbed during our reaction. We either release free energy or we consume free energy. And so, one, we don't really care what the actual value is here. Like, do we care if our free energy was 100 joules? No, not really. All it matters is if it went up or down. Like, the 100 doesn't matter. It matters if it went from 200 to 100, and so free energy was consumed, or if it went from 50 to 100 and free energy was released. So what we care about is the delta G, the change in the free energy. And so we've got this equation that relates our entropy and our enthalpy changes. We've got delta G, the change in free energy, is equal to the enthalpy change, represented, remember from last unit, by delta H. The enthalpy, delta H. The entropy change, for some reason, is given delta S. Don't know why it's an S, but that's the standard term for it. And the entropy term is delta S times T, because remember, entropy depended on temperature. At higher temperatures, the entropy change is going to matter a lot more. At higher temperatures, molecules, atoms are moving faster with more energy. Their level of chaos, disorder, randomness becomes a lot more important. So these two factors come into play here in this equation to tell us if a reaction is going to be favorable. Let's think about what delta G would need to be for a favorable reaction. We know favorable things are exothermic, so that would be a negative delta H term. And favorable reactions increase entropy, so we'd have a positive delta S here. We've got a negative term minus a positive term. That will always give us a negative number. So spontaneous reactions will always have a negative value for delta G. If we calculate delta G and we get a negative value, we know that that process is spontaneous at the temperature we calculated. If we get a positive value, then we know that that reaction is non-spontaneous at the temperature that we calculated. And so that's this key idea here that I just said. To get a spontaneous reaction, we're looking for a negative value for delta G. Here's an example. We're told that the entropy change for this reaction at a temperature of 298 Kelvin is 3 joules per mole K. The enthalpy change is negative 394 kilojoules per mole K, and we want to calculate the Gibbs free energy change to determine whether this reaction will occur spontaneously. Now, the one thing you do have to pay attention to in these calculations are the units on these two. Enthalpy change tends to be expressed in kilojoules per mole because they're typically pretty large values. Entropy changes tend to be in joules per mole because they're pretty small. We're going to try and add these together, so we have to make these units match first. Either this one needs to be converted to kilojoules or this one needs to be converted to joules. That's one thing that you'll probably almost always run into, and it's important to recognize that and account for it first so that you get the right answer. So we've got our formula for delta G. Delta G equals delta H, which is our enthalpy change, and we were told that value, negative 394 kilojoules per mole, minus T delta S. Our T is 298 Kelvin, our temperature in Kelvin. It had to be in Kelvin so that these K units would cancel when they're multiplied. So T times delta S, our entropy change, delta S, is 3 joules per mole K. Again, we had to make that kilojoules first, so we divided by 1,000. We moved the decimal point 3 places to the left to get that to be in kilojoules. Now we can plug into our calculator and solve. Don't forget to do order of operations properly, though. This is 298 times 0.003, and then that whole term subtracted from this delta H. Don't, if you plug it into your calculator in one line, you'll need to include these parentheses here. Otherwise, your calculator is going to subtract these two numbers and then multiply this one. You'll get a completely different answer. So remember order of operations. multiplication first, or include parentheses to tell your calculator to do that calculation first, then the subtraction. So we got a delta G value of negative 395 kilojoules per mole. Hey, the actual value doesn't matter too much. We got a negative sign. We know the reaction is spontaneous. And we could double check that to make sure it makes sense. We've got an enthalpy change that's negative, so we've got an exothermic reaction, favorable as far as enthalpy is concerned. We've got an entropy change that's positive, so chaos is increasing. It's favorable as far as entropy is concerned, so it makes sense that we got an answer of a spontaneous reaction. Both changes pointed towards spontaneous. All right, so just to bring this all together for this section, our changes in enthalpy, which we've been talking about in this unit and also in the past unit, and changes in entropy introduced this unit, can be used to explain why some reactions occur naturally and others do not. Just because we can write a balanced chemical equation doesn't mean that that reaction will actually occur. We have to check its enthalpy and entropy changes to see if it is favorable and spontaneous at a given temperature. All right, that's all the information for this unit. So, awesome job. Again, let me know if you have any questions.